Liquid-liquid extraction, LLE, is an important separation method in research and chemical analysis. It separates two miscible or immiscible mixture with the use of solvent. As a commercial process, it is frequently used in the chemical and mining industries and in the downstream recovery of fermentation products, for example, antibiotics, amino acids, and steroids. The process can be divided into two categories, in example, single stage and multiple stages. In this topic, we start with a single stage LLE process. Let's have a look at the definition or process in conducting a single stage equilibrium. The basic procedure for performing a liquid-liquid extraction is to take two immiscible phases, one of which is usually water and the other of which is usually an organic solvent. The two phases are put into a device called a separatory funnel, and compounds in the system will be distributed between the two phases. When liquid solution is mixed with the solvent, an intermediate phase M momentarily forms as the light liquid moves through the heavy liquid in the form of bubbles. In a single-stage equilibrium, the raffinate and extract are in equilibrium only once. The binary solution containing solute, which denotes by component A, which dissolve in a diluent or carrier, which denote by component B. The extracting solvent can be either pure solvent C or maybe contain a little A. So that's mean the composition of the solvent either unity or close to unity. The raffinate R is the exiting phase which is rich in the carrier B, and while the extract is the exiting phase which is rich in the solvent C. In the next few slides, we will look at a few types of ternary or triangular diagram typically used to represent phase diagrams. Equilibrium relations in extraction. When we talk about equilibrium relations in extraction, you should be understand about phase rule and triangular coordinates and equilibrium data. Phase rule is a liquid-liquid extraction system which has three components, that is A, B, and C, and two phases in equilibrium. While triangular coordinates and equilibrium data is the data of these three components which is in equilibrium and can be plotted into a ternary diagram to solve for single stage or multiple stages LLE. Typical equilibrium relationship can be presented in a triangular diagram. There are two types of a triangular diagram. The first one is called right angle triangular diagram, and number two is equilateral triangular diagram. Liquid-liquid system have three components, consist of component A, that is solute, component B as a carrier or diluent, and a component C as a solvent. There are two phases that will be in equilibrium, which is the extract and raffinate. So recap on your understanding about this definition. Extract is a solvent-rich stream, and raffinate is the carrier-rich stream. An example of liquid extraction system, benzene, water, and acetic acid. So benzene as a solute that is carried by water and extracted by using acetic acid. These are another two examples, consist of acetic acid, water, and isopropyl in the system, and acetone water trichloroethylene system. Triangular coordinates like in this diagram are often used to represent the equilibrium data for three components A, B, and C. So each of this vertex or corner is showing or represent pure component of A, B, and C. For example, here this is showing 100% of component A. This point M representing the mixture of a component A, B, C. Now let's have a look at the composition of component A, B, and C. Okay, there is a point here from M. For example, we are taking point M to the base of BC. Okay, so the distance here is actually giving the composition of component A and given by XA. So from this scale, we can see that this component A, since over here is 100%, that means until 0.4, it is 40% of a component A. Let's have a look at another distance that we have in this diagram. From point M to the base AB, okay, is giving the composition of component C or the solvent. So from here, it shows that 40% of component C, because 100% of component C is at the vertical of this diagram. And another distance from M to the base AC here, so this is another distance. It is translated to a composition of component B. These are the two typical representation of a phase diagrams. So let's have a look at this picture A, where in this system the solvent pairs BC and AC are partially miscible. So here inside the diagram there's a pocket which connected by a tie line. Inside this pocket is representing the two phase region, while at the outside are representing the one phase region. Typical examples of this system are styrene, ethylbenzene, and diethylene glycol. Another example is a chlorobenzene, methyl ethyl ketone, and water. Remember in the previous slide, we look at the triangular diagram or triangular coordinates. So this is an outcome of that plot using triangular coordinates, which representing three components of A, B, and C. Inside the pocket here, with the mixed point M, is a two-phase region, and outside of the pocket is a one-phase region. Typical example of this system is methyl ethyl ketone, water and acetone, water chloroform acetone, and benzene, water, acetic acid. Since triangular diagram have some disadvantages due to that special coordinates, so a more useful method of plotting three-component data is to use rectangular coordinates like in this diagram. So this is an example, a system of acetic acid, water, and isopropyl ether, and the solvent pair B and C, of course, is partially miscible. So this is an example of data which are taken from the appendix A324. So over here we can see that a water layer and isopropyl ether layer. So what does it mean? This water layer is actually a raffinate. Okay, and isopropyl ether layer, because isopropyl ether is a solvent, so this would be the extract layer. Yeah. Okay, and these are the composition of A, B, and C in the raffinate, and composition of A, B, and C in the extract. So this data is represented by this diagram at the left side. Let's have a look at this diagram. Once you already have this equilibrium data, then you may actually plot the concentration of the component C, yeah, concentration of component C on the vertical axis and A at the horizontal axis. The raffinate and extract composition, so this is the raffinate and this is the extract layer. The raffinate is represented by X and the extract denoted by Y. To construct this equilibrium curve of raffinate, so this is a section. If let's say you want to plot for this raffinate layer, so you have to use the data from the raffinate section to plot on this diagram. Next is taking the data from the extract to plot for the extract layer. While the equilibrium line over here is actually a plot of XA and YA. And where is the XA and YA? Remember that the extract is represented by Y. So A is acetic acid. Therefore, extract here is YA and this is XA. Okay, and you take this two data to plot on the equilibrium line, and this is just a 45-degree line to use later on for drawing the location of G and I. The concentration of a component B is obtained by a difference in component balance. For example, XB is equal to 1 minus XA plus XC, while YB is equals to 1 minus YA plus YC, because the total of XA, B, and C is equal to 1. The two-phase region here is inside the pocket and one phase region is outside the pocket. The tie line, okay, let me rub here. So here is the tie line. If you can see here from this diagram, you can see the tie line from G to I. Alright, so this tie line is actually developed via trial and error. So to obtain this line, you must first calculate for point H. Point H is equivalent to point M. Yeah? Remember, in the single stage mass balance, so you will have L1 plus V1 is equal to M. Alright, so M is the mixed point. And then this ether layer, is called the extract again, and the water layer is called raffinate. Okay. The point G over here is representing the amount and composition of the extract layer, and it is denoted by a V and YA YC, while the location down here, what do you have here? Okay, the location down here is I is representing the amount and composition of a raffinate that denote by L, and composition of XA and XC. To really sure and clear about this situation, terminologies, you need actually to be first clear about the main terminologies, learn from the introduction topic. For example, the feed, a raffinate, solvent, extract, as well as the principle of a liquid-liquid extraction process. Okay, so this is a summary on equilibrium data in rectangular coordinates. The first, solvent pair B and C are partially miscible. Concentration of a component C is plotted on the vertical axis and the component A is plotted on horizontal axis. The two-phase region is inside the envelope and one-phase region is outside the envelope. A tie line GI connecting the extract layer solvent rich with a raffinate layer that is a diluent rich. The solute solvent rich layer G is called extract layer and designated by Y, while the diluent rich layer or I is called raffinate layer and designated by X. For example, the mass fraction or concentration of C is designated as YC in the extract layer and as XC in the raffinate layer. To gain better understanding about this section, please see the details in section 12.5b and also to try later on example 12.51 and 12.52 from the textbook.